Good morning. So this is week 8, lecture B. Okay. So we finished LFT almost, and today we are going to start SSV. And for the SSV part, we are going to do the definition and concepts. So after that, we are going to say how this mu can be used for the mu synthesis for the controller design. So eventually this is the way we can leverage the mu. So structure singular value. So what's this? We're going to talk about this one today. So you can see the logical flow is here. I have uncertainty, so I have a structured, unstructured. We already talked about unstructured. We are going to talk about structured. There's a systematic mathematical vehicle to describe that, such that you can separate the knowns and unknowns. So you have a nominal plant. You have a pull out the uncertainties, and so you have TZW. So you have W in here and Z in here. So so you have here you have U in here, and here you have K. So this is all output, okay, Y. So that's basically is our view of robust control. So I told you that in our control system, the control is kind of mad process, okay? So modeling, analysis, and design, right? Design, okay? Design. Modeling. So I hope you see that here, modeling part is this one. Oh no, I need another color. This way. The modeling part is here. So the modeling part, basically we're talking about this part, okay? And analysis part, basically, is for this part. That's the analysis part, okay? And the design part is here. That's our design part, okay? Do you see it? Okay, modeling, analysis, design. So for the analysis, basically, we have already covered in the previous chapters regarding what? Regarding a robust stability and robust performance. Of course, we also talk about nominal stability and nominal performance, okay? So the underlying principle is a small gain theorem, okay? Small gain theorem, okay? So the basic idea of the small gain theorem is if the loop transfer function norm is less than 1, there's no way to be unstable, okay? Unstable. So now we are here in this new chapter, we are talking about how to pull out those uncertainties, okay? Pull out the uncertainties, okay? Such that we can leverage the structure information. Okay? So by doing this separation, we introduced a mathematical idea of linear fractional transformation, which has upper and lower, okay? Lower. Okay? So in this case, we are going to have M delta, and we have Fu upper, okay, upper. So when we write this one, what does this mean? We're assuming that when k is 0, we're writing this way is basically is a TZW. We write this way. It's a closed loop transfer function. Okay, so this is Fu. Okay, Fu. Okay, if this is 0. If this is 0, giving M, giving K, what is TZW? So the TZW here from W, so this is a closed loop transfer function, okay? This is usually used for performance assessment. Performance assessment. So that is M, K, and F, L, okay? All right, so you can imagine what I'm going to say next is if I have already a nominal system with a controller, okay? So it's kind of nested, like F, L, M, K, then comma, then do this FU is my TZW when you have both K and delta, right? So that's it's much more systematic, more logic, and more concise in notation. Okay, notation. So you can say that this can be used for analysis. This also can be used for analysis, assessment. Okay, so on and so forth. Okay, so on and so forth. So today we are going to finish. Maybe quickly review what we covered last lecture. Then we move towards the structure singular values. So the purpose of everything we talked about, the mu, this is also has a nickname called mu, okay? Mu has an official name, it's called structure singular values. Structured singular values, okay? Structured singular values. So basically we use the structure information. So for the purpose of less conservatism. Okay, so that's the whole purpose. So if you design a robust control and your uncertainty bound is this big versus this big, which is better? You need the smaller ones, less conservative. Less conservative. If you say something less than infinity, it's not going to help. Okay, sometimes the bound is just too high. So less than infinity is not going to help you very much, okay? So we need smaller bounds, okay? So with that, we are going to move to the slides part. And I'm going to unmute and I'm going to put the screen down. It should work. See, this is beautiful. So we went through this. So you have seen the contextual information here. Now we are going to go very quickly about what's left is this part. It's a very simple one, okay? Don't worry about it. Again, let me remind you, many of the operations, they have the corresponding MATLAB command. So you can play with it. So I have a really good advice. I'm going to upload that PDF for you. It's called Robust Control Toolbox User's Manual. User's Guide, actually, it's called User's Guide. Give an overview of what's in the toolbox, why they need this toolbox, what's in there, some basic concepts behind, so you know what's already there, okay? So you don't have to create your own. Like LFT, all these things are already there, and like even copram fractalization type of thing, it's already there, okay? So next. So we have seen this already, upper versus lower. So this is kind of block diagonal, also partition the matrix like this. So the upper and lower, it's similar. We can convert that. My job is to have, given this interconnection, and what is W2 to W2 to Z2? What is the W1 to Z1? So in the future, when I say TZW, you should have this picture. TZW, okay? So you have W as assessment reference command, and Z is assessment output. So there you have an uncertainty part, and you have a control part. So this is your nominal plant. And then what you care about is the TZW. TZW is the closed loop transfer function matrix, okay? So in this case, we haven't added a controller in here, but I'll just show you mathematically it's possible to put uncertainty up or uncertainty down, either way. But the partition, matrix partition and the formulation, the final formula of closed loop transfer function, and the format is different. So you can see this is M11 and this term, there's an inverse here, M22 and there's an inverse here. And to make this inverse mathematically legal, then we need consider this is well posed. Because once you have this loop in a MIMO setting, we have dedicated chapter talking about internal stability. So this is a requirement of internal stability. Okay? Otherwise, that kind of connection might not be legal. It will cause internal instability. Okay? But that, we're going to say something about, I said, why we have the name of LFT, linear fractional transformation. So this is, say for example, if you can write ABCD, you know ABCD, and this Q is something you do not know, and you want to pull out the D to write something in this separate the D and the ABCD. So there is a way to use the lower or upper LFT format to separate them. Okay. So the M matrix has a special format. So M or N, okay. So you can see the inverse could be this side or could be this side. So that is because of the matrix format. So you should distinguish about left inverse versus right inverse. Right inverse. Left inverse, right inverse. But don't worry about this format, you can derive it. So what they call the textbook is called simple algebra. Okay? Simple algebra. So it's not necessary to derive it step by step. So we went through examples like traditional feedback. We feel very familiar with that. I'm hoping that from now on, since you have learned robust control in the future, you should get more used to this format instead of this format. Understand? This format is just showing you the signal flow and the in and out relationship. And this format is focusing on separated knowns and unknowns. What is the changeable? What is not changeable? Okay, so this is changeable. Okay, you can do something, but the rest is not. Okay, that kind of format. I think I derived it briefly for you about this equation. So you can put this G in here and partition the Z and W like this. And then the rest is something like this. Okay? One of the idea to pull out this K, just disconnect the K. Just pull out. Okay? Just pull out, meaning you disconnect them, throw away. Then you end up with this. With that, you will be able to write something like that. Then you put it back again. Make sense? So when we say pull out, meaning you delete it first, then you add it back later. So that you can write this separation format. Otherwise, if you keep this one in here, it will disturb you, say, oh, the N goes to here, goes to here, goes to here, okay? That's not true, okay? Not true. The N will not go that way. Okay? So that's partition part, and there's another way to think about it is to have a state space realization of each of those blocks, like in previous slide, in here. So you disconnect this one, you have three things. You do all this state space realization, then you stack all this state vectors together as a bigger one. So then you end up writing this bigger X with AB1, B2, and C1, D11, D12. So this is actually for the first time you have seen probably that state space is no longer A, B, C, D. It is A, B1, B2, and we have C1, C2, and D11, and D12, D21, D22. This format. The reason is we may separate the U and the W. U may not be the same as W. W is used for performance assessment. U is the actual control signal. Okay? Then you stack all these things together, you end up with a state space like this, which is the same as this format. Okay? So you may ask, is this minimum? The answer is no, it's not minimum. The writing this format probably is for convenience. Okay, for convenience. So whenever you see this format, you know that these matrices are from this type of realization. By individually realize each one, of course, each one realizing here is minimum. They put together, it may not. Okay, it may not, because of other connections. But anyway, in the future, we will see that your state equation, output equation, and performance assessment output, or filtered output for performance assessment, Z. Okay? So again, let's see. So the Z is W and UF, V and UF. This is the filtered output and filtered input. Construct as a Z for my performance measurement. Performance measure, the output and control effort together. So if I don't care about control effort, you can set W1 is 0, okay? Makes sense? So general technique to pull out the W1, delta 1, delta 2, delta 3 is to pull out these deltas, pull out, then you delete it, okay? Pull out and you delete it. Then you make this matrix. So here is the real connected things, and there's a trick of marking what's the signal around this one. It should be U is output, Y is input. Okay. So then we are going to write the TZW. Okay. Z equals this. This is TZW, right? It's M delta. Delta written in this diagonal format, and it is repeating. You can see in two positions. So this is block diagram. Okay, block diagram. And you can write the closed transfer function FU M delta. If you have M, you have delta. Then in MATLAB Simulink, it will be kind of standard format. But the question is how you can formulate this M, how to write this M. Okay, there's a way to do it. The one of my theories, you pull out all these things, you delete them. Okay, you mark all these things, you delete all of them. Okay, delete it. Then you start to write down this in and out and check what's the M. So then from this you can write this. Okay. Then you can get the big M matrices here. You have vectors here, Z here. So then you insert this one back. Delta. The delta is in this form. Then the output, this is in and out, closed loop transfer function TZW. This is called TZW. So this format, I call it a TZW here. It's a LFT of M delta. LFT. So you can see this is a very general, very systematic. You'll always be able to separate that, you'll be consistent. Okay, so I hope you will practice this technique, okay? And in the homework. The same thing is true if we assume this is MSD, mass screen damper system, okay? Second order. And you have physical parameters MCK. So then MCK always with multiplicative uncertainties. Here delta M, delta C, delta K. And the tilde is the nominal value here. And, so the delta is very structured like this. Okay. So then how to construct your M matrix? You can use the same idea like we have shown before to pull out this delta. Okay. So that's an example for the real system. You have parametric uncertainties. You can also write this way. Okay. For high maneuvering example is a benchmark example. The system is giving like this, P like this. So then how you can get open loop interconnection matrix by pulling out the deltas. Okay? Following the same step. So you're putting out this delta and putting out this one is K, is your control. Okay, controller. Then putting out this too, then you are having something like this. Then you start to construct what is your G-hat. It's called nominal system, okay? Nominal interconnection system. So we didn't say that this is in and out from W to Z closed loop transfer function. So here they used closed loop interconnection. Yeah, I don't feel comfortable using the term closed loop here. Okay? Because it's not closed. We delete this one from the loop. Right? I don't feel this is nice. Okay? We'll probably just say interconnection matrix or nominal plant. Nominal plant M. Okay?
But that nominal plant is only in terms of the plant, right? I mean,
nominal interconnection. Okay, yeah, we still need interconnection. Otherwise, it's only this guy, right?
mm-hmm.
And then we need to include all these weights, weighting filter matrix.
Okay.
Yeah. So then you can construct the Simulink block diagram for this aircraft plan, and this is widely available. One of our projects will be like this. I'll give you the files. Probably still in the demo of Simulink in the robust control toolbox. So the aircraft model could be very nonlinear. Okay, nonlinear. So you say, oh, I want to do linearization and operational point, or linearize it to get an LTI system. Don't worry. They will give you, if you do linear model, they will give you automatically. They extract the Simulink model, or linearize the model for you automatically. So go and understand what is the linear model command, and they will give you all this A, B, C, D for you from the Simulink model. Okay. Okay. This is the last one we haven't covered. So say for example you have a P and K. There are two transfer function matrices with appropriate dimension. So you have a partition like this. So there's a called a star product. Okay, star product. So it's funny to see that there's only part of the case connected to P. So this is output get to the input, and then this is output get to this in. Okay, this is in. Why you feel you need this type of structure? So think about the control. Think about the system. Okay, you have a So say this is a system. This is your controller. So your system you want to control. So this is a controller give output you can control, right? Okay. But the controller will also need the output in here, while they also need some other external signal to drive the control. This reminds me what? Feed forward or tracking. Okay? So that will be able to add, it's not just the initial value problem, right? So you can access 0 and see how it gets down to the origin. In real world, your control objective may need this type of thing, W hat, external model. So by doing that, how you can construct, then probably you should, the internal structure should be something like this. And by doing that, you have partition here, you have partition here. Assume all this dimensionality is compatible. Then in the end, you can write this format. So you have 2 in and 2 out. So internally, and then you will have something like this because of this interconnection. Okay. So don't worry, we have a star P command for you. I remember. Oh, we didn't do that. Yeah, it's lost. There's a star P command, okay? Star P command in robust control toolbox to automatically make this connection for you. So we reviewed everything here. Let me remind everybody the big picture. We did a mathematical vehicle about LFT. Now we pull out this delta, and then the structure information will be kind of like revealed to us. Then next question is how we use this information to elaborate our characterization about the uncertainty bounds. Okay, so remember then you have a diagonal or block diagonal of the delta. Okay, then obviously it's not fully populated, it's only diagonal. So how we can leverage that kind of non-knowledge or structural knowledge to design our robust control or do analysis with less conservatism. So that's the key purpose of introducing the mu. And also the mu synthesis is also very practically useful. But in theory, our robust control can stop here. We don't have to learn. So in other words, chapter 10, in the end of chapter 10, we can stop. This course is over. Because we already have this all systematic way, you know. But then we have a chapter 11 until chapter 18. So we have 7 chapters after this. Okay. I want to give you pre-warning why we should not stop here. Although this is a very nice framework, so you have a less conservative, you have mu, and you use the mu to design a robust control. So there is a famous term, is called a decay iteration. I'm going to tell you that later, okay? So the mu synthesis through decay iteration, then you will get your robust control in the SSV sense. So unfortunately, this mu synthesis via the decay iteration, it may not give you a feasible controller. It may not exist. Okay, you characterize the structure, you can pull out the delta, did everything is nice. But according to the design of optimization, you may not be able to find a robust controller based on the mu synthesis. So this is bad news. Okay. How we can ensure we have a solution? Then we need to move on. We need to seek different framework. So this is a pre-warning. I hope you know that we are learning. This one is very useful. Okay, very useful. I agree, very useful. But it may not work in certain cases. Okay? So that's why we need something further. Say, for example, we return back to control parameterization. It's also known as a Euler parameterization. Basically, I have a robust controller. I have a family of the robust controller that can do the job, okay? Stabilize the system, but which one is the best? Then, so you basically make the robust controller parameterized, then you search the best controller. That's by 2 steps, okay? You find all controllers that can stabilize the system, which is a family of the system, okay? Then you pick up the best one, okay? So I hope I'm not confusing you. I'm going to come back to this philosophy again and again. So the controller, okay, design, okay? Controller design is a way of trade-off. So in traditional sense, the logic is the same. So you give a plant, G of S. You want to design a controller. First, this controller must make the closed loop stable. Second, the controller must achieve the closed loop performance, okay? So there are 2 steps in controller design. First step is to find a family of all such controllers that will stabilize the system. So let me add a little bit more logic here before we move on. Otherwise, you get lost very easily. Okay? For controller design, so I have 2 steps. Okay? The first step is to find this controller, all C of S, okay, that stabilizing G of S. Okay? So you have a G of S. You design a controller C of S, okay, so this one, okay. So you have all controllers, okay, stabilizing this, make this closed loop stable, right? The second is these for all stabilizing C of S, find the unique one. Find the unique one, C of S, that satisfies the certain performance. Okay? That meets the performance requirements. Okay, I hope this is very clear. So you have a plan you want to control, and you find the only one controller. You choose the one, and why this one, not that one? Both of them can make the system stable. So then it's because I have a performance index. That one is the smallest performance minimum. Okay, that makes sense. So that we can be unique. Okay, it can be unique. So we address the system stability. We talked about performance. Okay, and this is our classic control. Okay, our classic control. Yeah, you make the whole system stable, and then you pick up the unique one that satisfies your performance. Okay. But today we're adding one more. It's called robustness. Okay. So these things as an extension, but the actual point I want to make here is to justify why we should go beyond mu synthesis. Okay. I want to give you early warning, because otherwise you feel like, oh, we learned so much, uncertainties, unstructured structure, the mu, SSV, and based on mu, with decay duration, we can design the K. It's a happy ending. We should stop here. Okay. I'm saying no. We should not. The reason is if we go back and revisit the SISO control philosophy, is like giving a plant, the first step you find all stabilizing controllers. And how many of them? Answer is infinite, okay? You can find infinite number of C's that can make the whole system closed loop stable, right? Okay. Then you do to make, because it's infinity. So then the second question is make it unique. Make it unique. Want to make it unique, you need performance, right? So, for this step, how can you find all of these C's to make this closed loop stable? For those of you who took my mechatronics there, you should know. This thing is called Euler parameterization. Say for any of Q of S, okay? Any of Q of S that is stable. Okay, let's say RH infinity. Stable rational, which was a function or filter, okay? So if I can somehow write my controller expressed in this Q of S, parameterized by that would be nice. This is called parameterization. So Euler parameterization, we should say Euler controller parameterization. I express my controller in terms of another stable family. Any of this one will make the C qualified for stabilizing that. How to do that? Okay, how to do that? Do you guys know? I will leave this one to next week. Okay, I will leave this one to next Wednesday's lecture after the new synthesis. And so, because next chapter will be controller parameterization. So you can see the chapter 11, chapter 11, controller parameterization. You may feel clueless. Why we need a chapter like that? Why we need even talk about it? So the only when you can parameterize with something, you can optimize. Make sense? Otherwise, how can you find the only unique one in the infinite? Okay, make it unique. You need parameter, so then you search that parameter. Make sense? Okay. So in SISO parameterization is called Euler parameterization. In the chapter 10 is more general on the MIMO case. It's the space case. So sometimes it's also called Q parameterization. Okay, Q parameterization. Okay, and do you still remember this part? I usually will give an oral exam to PhD students. So be careful if you put me on your computer, I'll ask you. Say, I have an open loop stable G. Okay, so you find a controller to control this, but if the controller C don't put it in properly, you will make this system unstable. Okay, even if open loop this is stable, make sense? Yes, yes. But you choose one, make the open loop stable, the closed loop also stable. How many such C's? How many such C's? The answer is infinite many. Okay? Now next question is, can you write down all of these C's that make the system stable? This question can be answered by using Euler parameterization. It's surprisingly simple. Surprisingly simple. Okay, I'll let you know next time. Let's put it here. The reason I'm doing here is to prepare for the next lecture. But today, let's talk about mu. I'm not downplaying the mu, but the mu was thought a big achievement in robust control. But later on, people feel like we have something deeper to work on. So, well, we are going to go back to the slides. So you can see there are so many topics in the mu and the mu synthesis. So it is a very general framework. And if it works, it will be extremely nice. So I hope you will pay attention to next slide. Okay, because it's very important to establish that concept. Okay. So then we talk about what is the mu synthesis. We talk about unstructured uncertainty. I think this part is already done. Okay, we're talking about structured uncertainty. So basically today we are going to spend time on here. Okay, then we finish. Okay? Then we finish. So in the next 30 minutes we are going to focus on that. But before that, let's to review what we have. So this picture is exactly this picture. He used P, I use M, that doesn't matter. So we care about the system performance from W to Z, so TZW. So in this case, you have three parts. So this is a vector, this is a vector, this is also a vector, okay? Vector, vector, vector. So you have three vectors in here. So that's why you can do a partition of the P into 3 by 3 parts. The sizes may not be the same, okay? The sizes of this signal, this signal, this signal, they may not be the same, but they are all vectors, okay? Vectors. So when I write this way, so you're going to see from W to Z, you can write W to Z. What you do is lower LTF, lower linear transform, a linear fractional transform, LFT, is PK. So then, comma delta, you have the upper LFT, linear fractional. So you can see like exactly I put it in here. Okay, you have L, you have U. The same thing is true. You can do this one first, then you do the lower. So you can do upper LFT or P delta, then you do the resultant one. Okay, you have another one. It's called FLK. So lower LFT. Okay. So from TZW point of view, from W to Z, so these two forms are the same. Okay, are the same. So you can see, isn't this very beautiful in terms of using LFT? You make things very compact and easy to understand. Yet you have controller, uncertainty, nominal system, nominal interconnection, nominal models interconnection matrix in a nice structure. Okay, so this becomes approachable. Okay, go ahead.
These methods, I mean, we only can use them. I mean, this is for linear systems, so it should be like everything should be transfer functions. The controller,
yes.
The controller.
RTI.
Yeah.
RTI.
I mean, what if we have a
transform
non-linear
image.
controller?
No, nonlinear control. The nonlinear part can be lumped in here. So you give a bound.
But always some optimal controllers. I mean, they're based on like.
Exploring the explicit nonlinearity form. That's another subject area. It's called nonlinear control.
Yeah.
Okay. Even that in nonlinear control, you have nonlinearity. You know it, but that nonlinearity also have some uncertainties. Okay. So therefore, there are subject areas called robust nonlinear control. Robust adaptive control. Okay? But it's very funny that I discovered, so you can ask anybody. Robust adaptive control is to make the adaptive control more robust. But what is adaptive robust control? So you got a robust control, then make it adaptive. What are you doing? You updated the P based on some new information. We have a more modern name for it. Do you know what's that? It's called big data driven. Make sense? Okay, big data driven. Basically, using big data, you drive and update the P from time to time. You have another mechanism to update your model, to redesign everything, then deploy. So that kind of adaptation. So in principle, robust adaptive control and adaptive robust control should be different. Okay? What we are learning is robust control. We are not learning adding robustness to adaptive control or to nonlinear control. So I know why Sina was asking this, so don't get confused. But if you ask, say, oh, this framework, robust control for LTI system, looks great, but can we do nonlinear system? I answered this question from day one, right? Don't worry, your time varying part, nonlinear part, can be put into here, and assuming you can bound it. Okay, they are bounded, so then it's okay. If this is unbounded, it's huge. It's not. You probably need to shift another framework. You need a big data driven to refine the model such that you extract more LTI model into here and make this one smaller. This process of sharpening is just like sharpening your pencil. The sharpening process is the right way for the next stage of robust control, driven by big data. So that's why people talk about uncertainty quantification, UQ. So basically they have a metric to tell, have you hit to the bottom line that's the best you can achieve about the model uncertainty. Don't make any more efforts to sharpen it. It's already there. This is already at the bottom. There's already at this lower bound. Is there a such theory for that? Yes, there are something like that. It's called information theory. In the information theory, then there's a way to decide what is your bound, lower bound of your delta. It cannot be smaller than that. But this is beyond my class, okay? But it's very interesting to keep asking, can we make the uncertainty bound smaller? Then you need to ask, what price do you want to pay to make it smaller? That's another question. So there are a lot of trade-offs, not only just mathematics, okay? So this type of separation is, from now on, you should feel very comfortable about this framework, okay? Instead of asking for a controller plant, this kind of framework previously. And using LFT, and again, I say the MAD, modeling analysis design, okay? So you can make an analysis, giving controller, given P, how robust, how much robust I can sustain. So you can make the P and the K absorbed, combined as an M matrix, okay? Right. So you can do still upper LFT to get this TZW, okay? And this TZW should be the same, okay? Should be the same. They simply put this guy as FLPK, this one as M, okay? This one as M, okay? So this is mainly for analysis, okay? So we can check, we can evaluate whether the controller is robust to the given uncertainty size. So there are a lot of questions we can answer. This is a block about analysis, okay, and synthesis, okay. So if you assume your, depending on what you assume, so you assume your, let's look at this one. Don't get very confused about this thing, okay? Let's still use small gain theorem to think about it, okay? So we probably will go to here later, okay? Here later. So basically, we are doing is perturbation is here, okay? Perturbation is here. So it's infinite norm is less than 1, okay? And the input signal, this W now, here is an input signal. This is a signal norm. This is a system norm, induced norm, okay? So delta is a system. System means system has input. This is a system, this is a system, this is also a system. System has input and output, okay? But for this one, W is not a system, W is a signal, okay? So W is a signal. So I want to make sure you understand here we are talking about input assumption is input is 2 norm is less than 1, okay? But it's always less than 10, can I do it? Sure, you can do rescaling. You can lump that one into your filter, weighting filters, okay? So we want the overall system, overall performance requirement is to make it internally stable. Then only thing is if you want perturbation, assume perturbation is unitary and less than 1, then it amounts to M11, the infinity norm is less than 1. Okay, this is the test protocol you have to satisfy. Okay. Then, what is the synthesis method? How to achieve that? You must go to H infinity. This is the worst case scenario. Worst case scenario. Another one is so you can see that I want the stability. I didn't care about what is my output. So Z is my output signal. I didn't care how big is my output. I only cared about my internal stability. So the M11 side must be less than 1 to ensure the internal model principle. The small gain theorem that the overall system is stable. Okay, so you use H infinity principle to design the K. You will be able to get it. So we have seen this before. Okay, seen this before. Okay, we didn't care about the structure in the delta. Okay, we can also address several other things, but this will be in a later chapter. So this is, to me, is like you don't have uncertainty. Okay, don't have uncertainty. Okay, you have no uncertainty. This is no uncertainty. Okay, so then you want to ask. Giving the input is unitary, or you give unity is a delta. Okay, it's impulse, unity impulse. Okay, so then I hope my output is 2 norm square is energy. Okay, the energy is less than 1. The 2 norm less than 1. So you have different ways to design that. So this table can be long, because you have different assumptions about your inputs, you have different specifications about your outputs, and sometimes the outputs, the Z, might include your real output and your control effort as well. Okay, we have seen that. So this to me is all nominal performance. Okay, nominal performance. So anyway, in an unstructured case, we didn't assume the structure in this delta. There isn't much you can do about synthesis, analysis. So these 2 words, analysis, is giving condition and check whether the result is, or whether some condition is satisfied. That's analysis. Synthesis is, I want this one to be less than 1, how to design a K. So synthesis is more like design, okay? Control design. So we use design, not synthesis, in our control. Because synthesis is like workflow. Given this, you can get that. Given that, you can get that. Step by step, you come out of control. So that's called synthesis. Okay. Of course, it's design. So that's for unstructured. Okay, unstructured. However, in a structured sense, we can pull out the deltas like that. Okay. So you can see that we are pull out this one here. So this is small delta. So I put back to this S, so showing that this is transfer function matrix. Okay, transfer function matrix. Previously we didn't put this S. Okay, but doesn't matter. Okay, so we have diagonals here. So we have scalar. We also have small bulk submatrices. Okay? And within each of the matrix, so this is a matrix, transfer function matrix. Within each of these, okay, within each of these, it could be fully populated. We don't know what's inside here on that matrix. It's unstructured. Let's say that way. But if you have block diagram or something like that, this thing is already called a structure. So this delta of S is called structured uncertainty set or family. Okay? And of course, we assume everybody is RH infinity, so proper, not necessarily strictly proper stable transfer function matrices. Okay? So that is our family here. And of course, each of them, we can scale it such that infinite norm is less than 1. For scalar, it's very easy. Just magnitude and over all omega, okay, you check what's the peak point. That peak point is your H infinity norm for scalar transfer function. But if this is a matrix of smaller submatrices, so what you already learned, what you do is you do maximum singular value of this guy, delta J. Then you scan the omega, okay, check the highest point. That point is my infinite norm. I assume everybody is less than 1, but you may say, again, this is without loss of generality, okay? Because I can always make those normalized to 1, and those coefficients will be absorbed into that W weighting filters, okay? So don't worry about this one. You don't feel comfortable, this is 1, you should not feel uncomfortable. Okay, so it's always possible for the M matrix linked to that. So these are connections with all those uncertainties. So there's a M11 partition, and 2-1, 2-2, 1-2. Okay. So this is in and out directly connected. So this is M11. Okay? Others are just a coupling. Okay. So stability condition, they only need this guy to be less than 1. Okay. So this is according to what? Small gain theorem again. And in this case is sufficient but not necessary. Make sense? Sufficient may not be necessary, okay? Because it is maybe way conservative, because we never even talk about this diagonal structure. We assume everything here is less than 1. It's a big matrix. Yeah, this whole delta S as a big matrix. Okay? And this big matrix also with maximum singular value less than 1. Okay? So if you do this, then in terms of small gain theorem, you have for sure it's a robust stability condition satisfied. So it's sufficient. Okay, sufficient. So that's great, but ignore the structure in here. So how we can, so this is sufficient but not necessary, okay? Necessary condition then is just to test each of the delta or the block, full block delta. So this is a fully populated delta, okay? Delta or delta, okay? Individually, and assuming no uncertainties in other channel, okay? Then basically you want this M11's block, or also at that diagonal term, okay? I diagonal term, okay? Will infinitely not less than 1. So this is necessary. It has to be true, but you cannot say this system is stable yet. It's not sufficient, but it's necessary. Okay, I hope it's not confusing. So sufficient is good, but it's conservative. Necessary may not be true because we ignore all the interactions between all these deltas. Okay. So interesting. So I hope you understand the sufficiency and necessity here. Okay. Both of them are not very good. Okay. So can we have something in between? Can we really have something that is less conservative and sufficient? Okay. Well, here is some argument called what do we mean unstructured? Okay. What do we mean unstructured? And what do we mean structured perturbation? Okay, we need to look at this one very carefully in the next 10 minutes, okay? So think about this nominal plant. So then you find out smallest, the unstructured, there's no structure imposed on this set, okay? Such that the maximum singular value of this guy, okay, then make this determinant of I minus M delta is 0. Okay. So it may not be obvious to you, but this one basically is a well-posedness condition. Okay? It should not be 0, but I increase the delta such that it hit this well-posedness boundary. Okay? So when I hit that, so this is the smallest delta. It's sigma watt delta makes this one not well posed. Okay. Okay, that's smallest delta. Okay. Of course, you can make the delta really big. You can destroy this well posedness easily. Okay. I want to find out the smallest one such that this is. If you keep doing smaller, then it will not be 0. Okay. That sense. Okay? So in this sense, we find uncertainty delta makes this determinant 0 is yield posed, and find all those delta make it yield posed. Okay. And check all the maximum singular values and give that minimum infimum, that's minimum possible constant. So this minimum constant is this guy, the sigma bar. Among all the sigma bars, I choose the smallest one. So this is consistent to the smallest delta. So in language, in math language, is basically saying that. So this is a sigma bar, this is a set. This set depending on this condition, and this delta is from this space. So then there are lots of choices to make this one, and among many choices of the delta, sometimes maybe delta is only one choice. Okay, but among all different choices of delta and satisfy this, then I choose the smallest maximum singular values and denote this one alpha minimum. So this alpha minimum, basically, you can say, oh, I'm trying to scale this guy. You can scale it. The alpha is like scale the delta, bigger and small. So basically, I choose all those alpha. That makes this guy is 0. At the same time, the sigma maximum single value less than 1. Okay, and it turns out that the alpha is the same as this guy. Okay. 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 So it is quite interesting that you have a maximum singular value of m times delta in here. You check its rho here is spectral radius, okay? Spectral radius. And under all possible delta, its maximum singular value is less than 1. Then this one, the maximum of this the spectrum radius is 1 over alpha minimum here. And this inverse actually is sigma bar of m. Don't you see there is m delta small gain theorem here? Okay? Okay? I see it. So alpha minimum times sigma bar here must be 1, less than or equal to 1. Okay? So that's why you have this relationship. Okay? So with that in mind, think about this delta times alpha is kind of destabilizing effect. So if you change the delta to a point, okay, we'll scale it by alpha, to a point, the system will be no longer internally stable. Does not satisfy that determinant not 0. Okay? In that case, we can describe what is my smallest destabilizing delta. Okay? Destabilizing delta. Again, I don't see this is very hard to accept. Basically saying that maximum singular value of the original m, one of this one, and 2 unitary directions. Okay, unitary directions. And this one you will make this 0. Okay. In our textbook there is a more detailed derivation. So basically, it's a spectral eigenvalue decomposition here. So you can write it as directions. Okay. This is the biggest one. This is the second one, third one, and so on and so forth. Okay. So again, I hope this whole thing. I hope you remember. Time this one less than 1 is small gain theorem. And this guy is the scale of the alpha that can make change the alpha. You can make the system not well defined or not internally stable. So we define the uncertainty makes this uncertain. So this is alpha minimum, okay? This is alpha minimum basically. So this is basically writing the alpha minimum inverse, okay? Inverse. And this one is this one. So the largest singular value of m is decided by the alpha m, okay? Alpha minimum. And alpha minimum is defined by what they call the sigma bar, this one. Basically, the smallest uncertainty in the sense of sigma bar, such that the system is not well defined. Okay? Well posed, okay? So this alpha minimum, and this one says, given a nominal system, your uncertainty has some sort of bound, okay? Some sort of bound. Or in other words, you have an uncertainty set, okay, delta. If you already have uncertainty set, delta, okay? Then we can define your nominal system's maximum singular value. Okay, so large is a singular value is defined together by this format. Again, the whole thing here, I can see this is small gain theorem. Okay, small gain theorem. So to make the whole system well defined. Okay, well defined. If not true, it will be not well defined. The system is not internally stable. So that's for unstructured perturbation. There isn't anything strange in here. We are so familiar with this. So the next slide is talking about structured perturbation. So please take a quick look. We are going to come back on this. So with that, remember we didn't put any structures on the delta. Now we have a structure and there's a block diagonal, a scalar. Okay. So this is a scalar. This is 1 by 1. This is some small matrices. Okay. Okay. Mj, Mj. So this is a scalar as well. So we can argue the same way. We can argue the same way. And remember, we are doing delta with bold-face delta. This is bold-face delta. It's an uncertainty set. It's called structured uncertainty set delta. So get this delta not arbitrarily. What's the difference of previous slide? Is the delta here is from CPQ. This is C. It's very broad. But now we are not getting the delta from that C. We get the delta from this structured set. It's a subset of the C. Okay. With that, we can do the same argument about define alpha minimum. So which is we find the smallest maximum singular value for the delta. That's the delta will make the system not internally stable. Okay, and this is the same argument, but from different set. Okay, different set. And so this alpha minimum, okay, inverse. So we can argue that from this structured set, make the sigma bar less than 1, and the spectrum radius m delta is still defined by that. Okay, and most important part is here that it's guaranteed that this guy is definitely less than the maximum value of delta m. Okay, so go back to the slide. Go back to the slide. What do we have? It's strictly equal. Okay? Strictly equal. And here, because of the structure, then we have chance to be smaller. Okay? That's the beauty. The everything we start from here. So start from now on, we start to call this guy 1 over alpha minimum as SSV, or structured singular values. And this will be our starting point to design less conservative, robust control. Okay? So we are going to stop here. I will let you go. We are going to continue Monday. And today I will be in office. Please join me anytime after 2, okay? All right. So I'll send you